Engineering 305, we're still in Chapter 7. We are banging out sections 8 and 10 on principal stresses and stress concentration factors. There are no learning objectives or equations. I think these are sections that normally I would skip, but I just want to touch on them briefly. Maybe this will take all of 5 minutes, but I want you to see what the issue is and why they have sections about this. We can learn from that. Um, from example problem 711, they work this problem. They talk about it, but we've had our shear stress, or our normal stress, sorry, which is distributed linearly. So this is our normal stress. And then we just did a section on our shear stress where we didn't have shear stress in the web because it's all very stiff. But then when we got to, because we have this great broad distributed, it's got a big wide section that we have distributing that shear stress, lots of area. But when we get to the web, the shear stress is high. So here's our shear stress here, and it shows up high in the web. So at the junction between this spot, between the web and the crossbar, that's where we get the both. We're very much at the towards the high end of the normal stress, and we're doing okay for the shear, and so we get a larger principal stress. So if we continue to look at their example and show you the rest of it, what you'll see is at this section at the bottom edge, they go over and they calculate, okay, here are now the principal stresses. Well, that value for the principal stress is 132 megapascals. That compares to 122 megapascals when you just look at the axial stress. That also compares to 61 megapascals when you're looking at the shear stress. Now, if you remember, if we go back for material properties, if you think about a maximum normal stress failure theory, the shear stress, and I know you're going, what? Shear stress could only be half as high as the normal stress. And so you're already seeing that it could fail either way, depending on exactly whether that material is brittle or ductile. And this isn't that far away from either one of those. So yes, we have to be careful, but now I'm going to say if your design is within 5 or 10%, we may want to think about how we're doing our design. If in this case it's 7%, I think you're going to want to use some more sophisticated tools. I think that you may want to go to maybe you could go to a finite element analysis or some other code to help solve this, and they're going to give you those answers, and they're going to calculate both of those stresses and link them together. And we could make that an assignment, but we won't. So that's why this is a section. It's interesting, and it's not something I've spent a ton of time on. They also have, what I found is, if you go back and look at the systems we were looking at, our shear stresses were actually very low. And they became a problem because we had wood, which had much lower material properties in that shear direction across the web. So then it was interesting. But for a normal problem with normal, I don't think it's often a case where we're too concerned about it. So, all right, there's topic 1. Let's move to topic 2. Topic 2 is stress concentration in beams. Now, you should know we've done stress concentrations. You've looked at how they work. So the only thing we've got is now we've got new charts. And what is interesting about the chart, very clear how we're loading that. So those are flexing that way. And then this is an interesting note here that I'll highlight for you. These factors are for flat bars, but may be used for circular shafts with turned down sections, or this one says with turned grooves. So this applies to either one. That stress concentration is going to look the same whether this is a flat bar or whether it's a circular cross section. So I've got stress concentration factors for notches, for step down, for holes, and that looks like that's for grooves too. Oh, that's a notched bar. Really, it's interesting that that's different than this, but and maybe you dig into the details and it's not that much different. Oh yeah, it is. They're loading that. They're loading that 90 degrees from how they're loading this one. This is perpendicular and this is, I'll say, parallel, but that's not quite the right way of thinking about it. Anyway, those shouldn't take you by surprise. I have not assigned any homework problems on these because you do the calculation, you look up your stress concentration factor. It's fairly straightforward. So um, we're good. We're good. One thing to note on the previous slide, all of those stress concentration factors were based on KT, which is the smaller area. We did have some conversation about KT versus KG. KT is the smaller, it's the net area, not the gross area. Um, and that's all I have to show you. I do not have, normally I would have a next slide that says what's next, what the next presentation. There's no example problem that we're doing here, so whoop, we're all done. The next presentation is actually going to be on beams of two materials, where we have a beam that is made from wood and aluminum, or wood and steel, some composite sandwich going on. I find that to be an interesting topic, and so we'll spend a little bit of time on that. Hope you're doing well. I'll see you, well, I won't see you for a week for sure, because you can probably hear it in my voice. See ya.